तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 50 in mechanical measurements. It will also be the last lecture in this series and the second lecture in module 5. In the lecture number 49, we gave few general remarks on measurement of quantities, and specifically we considered the gathering of data using electronic circuitry. Of course, we have not done a very great job of it because it requires much more time to develop in full extent, but we have tried to give a flavor of what is involved. So, in the present lecture, what I will try to do is to look at a few cases and then see how we can go about making the measurements and also choosing the right kind of instrument for the purpose of making the measurements. So, the first example I am going to take is with respect to calibration of a thermocouple, and I am going to discuss how it can be done when a data logger is available to us. The principle of calibration itself we have explained to some extent earlier on. The need for calibration, of course, is to make the particular instrument come into agreement with a standard instrument. So, in this case, if I have a thermocouple of a particular type, I would like to see whether it is in agreement with a thermocouple which is standardized or calibrated in a standards laboratory or by a third party who is not involved in your particular activity. So, an independent check on the instrument is required so that we can rely on the measured values. So, the one way of doing it is to compare it with another thermocouple of the same type, but which has been calibrated by another in another laboratory which is acceptable to everyone. So, that is one way of calibration. What we are going to discuss today is not exactly that one, and I am going to do a slightly different way of doing it. What I will do is, instead of comparing the thermocouple with another thermocouple which is standardized, I will compare the thermocouple output directly without worrying about the nature of the thermocouple, its type and so on, which is totally outside our purview. What we will do is we will try to compare it with a secondary thermometer, another thermometer which I will call as the precision reference thermometer. If I look at the sketch here, this is the precision reference thermometer which is accepted as a standard as far as this particular calibration is concerned. So, I will take as truth whatever value of the temperature is indicated by the precision reference thermometer, which itself may be calibrated or certified by a standard laboratory. So, that is the way we are going to go about it. So, what I will do is I will subject the thermocouple which I want to use in my experiment, I will expose it to the same temperature as the precision reference thermometer by putting the two together in close proximity within a constant temperature bath. Okay. So, in principle, whatever temperature is indicated by the precision reference thermometer must correspond to a certain voltage developed by the thermocouple under calibration, and I am using it in a form without the reference temperature being at the ice point. That means that this calibration will be valid as long as the temperature of the data logger is at a uniform value, which is not going to vary with respect to time. If however, the data logger is going to be exposed to different temperatures because the laboratory temperature varies over a period of time, this calibration will of course be not totally correct. So, that will be a secondary issue, but here what I am going to look at is only without having a reference junction. Or another way of doing it would be to have a cold junction compensation within the data logger, because many of the data loggers do come with such arrangement, so that I can use that signal to correct for any variations in the room temperature. So, let us look at how this can be done now, having described the methodology we are going to adopt. So, I am going to just look at the data logger as a black box, and of course, I will describe more fully in the subsequent slides what this data logger does, how it gathers the information. So, what I am doing is I am comparing the reading of the precision reference thermometer. In fact, I am not comparing, I am calibrating the thermocouple by just equating or assigning a temperature on the precision reference thermometer to a voltage which I am going to measure using the data logger. So, it is just like a conversion factor or a conversion from one value here, voltage value here, which is of course will be in microvolts or maybe in millivolts, that will be compared to that will be assigned a particular value on the precision reference thermometer. This particular way of calibrating a thermocouple is actually valid for small ranges. It is okay to do this one. So, that is why I have written here calibration over a small range of temperatures. It is okay, because we may even assume that there is broadly a linearity in the scale, and therefore, I may do this calibration by choosing only a few temperatures. For example, I can take the ice point, I can take the room temperature, I can take some other elevated temperature like boiling water. So, 2 or 3 different temperatures can be used in the constant temperature bath, and corresponding values of the temperature indicated by the precision reference thermometer can be assigned to a particular thermocouple output in terms of millivolts or microvolts. So, I will just say there is a correspondence between the output of the thermocouple, which is of course going to be measured by the data logger, and the value indicated by precision reference thermometer. Okay. This calibration is not like calibrating one thermocouple with respect to a standard thermocouple, which was also already explained earlier when we were talking about temperature measurement. So, we will not go back to that. So, let us look at the kind of data one is going to get. So, what I have done is I have taken actual data which was gathered in the laboratory. So, typical calibration over a small range assuming linear response. In fact, we found that the linear response is pretty good, and we are talking about room temperature to about 100 degrees, that is the range maybe a little more than 100 degrees. So, I have just shown 2 points corresponding to a low value and a high value. For actual calibration, if the low value happens to be room temperature and the high value happens to be, let us say 100 degrees or a little more than that, it is advisable to have several temperatures in between. For example, if you consider this as the full scale and this as the 0 or the reference value, I should have 3 or 4 between these two limits, not coinciding with the end values. So, in this case, if the 100 degrees I have taken here, it means that I am going to use this for a temperature a little above that, maybe 120, 130 degrees or so on this side, and on this side I am going to use up to about 20, not necessarily with respect to up to 0. So, up to 20, therefore, I have chosen these two within the range. So, the temperatures at which I am going to calibrate, I am going to compare the output of the thermocouple with a precision reference thermometer must be within the range, not at the bounds of the range, at the boundaries of the range. Of course, I have taken only 2, assuming that the response is more or less linear. In fact, what I have done is I have taken 11 thermocouples, and I have taken the average behavior of these 11 thermocouples and then made a simple plot of the temperature calculated based on this linear relationship, and the linear relationship of course is given here. I am using the formula given here as T equal to this constant times the output of the thermocouple 25,253 times V plus 40.718. This is the formula which corresponds to this particular straight line, which is the average of 11 thermocouples. Of course, each thermocouple would show slight variation with respect to this value, and what I have given here is a mean for all the thermocouples. And the blue line I have indicated is what is called the parity line, which is already known to us. It represents parity between the calculated and the reference temperature. Of course, in this case the scale of the figure is such that we do not see much of an error between the thermocouple and the reference temperature. Of course, they must coincide, because whatever calculated temperature should be corresponding. This is just an equality. This is nothing really. The only point is I have taken the mean of 11 thermocouples and they seem to follow this rule very well. In fact, all thermocouples do not follow the exact values given here. So, they have some variations amongst them, and the mean value on the average, there is an equality between the calibrated or the calculated value and the reference temperature. That means this figure is really giving you only part of the answer. The correct answer is here. So, what I am going to measure is this value V. This V is going to be measured by the data logger or gathered by the data logger. So, how we are going to do that I will show in a little while from now. So, we measure this V, and then you can say that T as a function of V is a linear function. This is some kind of a transformation from V to T. So, an arithmetic operation is required where you have a parameter. This is a slope parameter 25,253 and the intercept parameter 40.718. So, you see that this is such a just a line y equal to mx plus c, m is the slope and c is the intercept parameter. So, what is it that we have achieved here? We have not done anything. We have just made the temperature indicated by thermocouple equal to the temperature indicated by a reference thermometer, which is highly accurate, highly precise, and we have simply mirrored the values which would be obtained by using the reference temperature reference thermometer onto the thermocouple. Therefore, the actual thermocouple behavior in terms of its Seebeck coefficient and so on, that does not enter here. We simply have a comparison. We have mirrored the values given by the precision thermometer onto the measurement given by the thermocouple. So, this is not a calibration in the strict sense of the term. It is actually making the thermocouple equivalent to a precision thermometer. So, this is a different way of doing the calibration. So, let us look at the data logger and see what it can do. So, what I have done is I have taken the data logger Agilent, it is called Agilent Bench-Link. Hewlett Packard is the manufacturer of this one, and what it does is what I have shown in this slide is the graphics setup. That means that you can set up all there are several channels and you can see the channels are named. It is not very clear on the monitor, but this is channel 1, let us say this is channel 2. So, several channels are possible and each channel can have different quantities indicated. For example, I can have voltage, I can have current, I can have some other quantity here. So, this is units per division I can specify here. I can also switch on or switch off the channel. So, in this case this channel is on, these 2 channels, these 4 channels have been switched off. So, what you see here is a virtual instrument in some sense of the term, because whatever is happening in each of the channel can be actually followed in real time. So, the next slide shows how we set up the data logger for scanning the data. What is the scan? Because the data logger has several channels, each channel has to be measured at a definite in a definite way. Suppose I have 4 channels, I cannot measure all the 4 channels at the same time. So, what the data logger will do is it will scan, it will go to one channel, make a measurement, go to the next channel, make a measurement. So, in a series of measurements will be made in time. Of course, the duration between the channels or the when it switches from one channel to other channel can be very small. That means it is almost like instantaneously at the same time all the channels are scanned. Okay. So, in this case let us look at some of the salient features in this one. Unfortunately, the numbers may not be very clear, but I will read them out. So, I have the name for the channel, I can give any name. For example, this I have ticked this channel, that means that this is being used. I can give a name here, I can name this channel, so that I can note down, or I can immediately find out what this particular channel is doing. It may be measuring simply a current or a voltage, or it may be measuring a temperature. So, I can say this temperature 1, channel number 1 corresponding to temperature from thermocouple 1, for example. I can write the thing here. The range is auto, that means the instrument will determine what is the maximum and the minimum, automatically it will change the range, so that you do not have to intervene. The resolution, this is the most important thing. We have got a 5.5 digit or 5.5 digits resolution. I will discuss it briefly on the board, and this happens to be the default for this particular channel. For all the channels the default is 5.5 digits. If you want to change it, you can change it to a lower value if you want. And here you see the gain and the offset. Actually this is nothing but your slope, and the for a straight line behavior this will be corresponding to the slope, and this will correspond to the offset or this intercept as we talked about. In this case I have labeled it voltage DC. So, this channel is now available to measure output in voltage DC with a 5.5 digits resolution, and we can immediately will see on the board that this is suitable for measurement of voltage output from a thermocouple. Why is it so? Let us just look at that. So, the resolution we say it is 5.5 digits. What does it mean? It means if I have a number like this, it has got 1, 2, 3, 4, 5, 6, the number can be having 6 places, and this can go from 0 to 9, this can go from 0 to 9, this can go from 0 to 9, 0 to 9, and this can be either 0 or 1. So, these are 2, 3, 4, 5, 6, these digits go all the way from 0 to 9, and the very first one goes from 0 to 1. So, this is called, this is 5 full digits, and this is called half digit. The reason why this terminology has come, 5.5 digits, is actually the following. In the olden days, when voltmeters were made, digital voltmeters, they always had, for example, it will have a range of 3 volts or 30 volts or 300 volts. 3 volts means you can see here 0 to 1, instead of 0 to 1 it can go up to 0 to 3, and 3 is nothing but 0.3 is nothing but logarithm of 2. So, that is how the 5.5 digit idea comes. We will just show that in a moment. So, the resolution of the instrument, you can see now, if I represent the output in the form of 6-digit number, 1, 2, 3, 4, 5, there are 6 digits. Of course, 1 is a half digit, that means it can go only up to 0 to 1. I can have a minimum, of course, I can have this. This is 0. I can have the maximum, I can have 1, 9, 9, 9, 9, 9. So, you see that this is different, this is different from 2000 to 200,000 by just one digit in the last here. So, the resolution is actually one digit in the one place in the last digit. So, the resolution is actually 1 unit in the last place. It is also called, this is the last digit or the last place, that is 1 unit in the last place. Okay. So, that is the reason it is actually, you can see this 1 unit in this, nothing but 100, this is 1 followed by 5 zeros, 1 in 10 to the power of 5 here. Okay. So, what it means is that the data logger which I showed is capable of find half digits resolution. So, that is what it means. Okay. And in the next slide, I am showing how to enter the conversion formula. You remember I showed an example earlier where the formula was here in the form of t equal to 25253 into V plus 40.718. This is the number I had. So, what I am doing is I am entering this formula into these boxes. So, I have got channel 1, 2 up to whatever number, 10 is left out. So, 11 thermocouples are there. So, channel 1 to 9 and then 11 and 12 all have 5.5 digits resolution, and all these are given the gain values. You see that the gain values actually vary slightly from the mean value which I gave earlier. 24623 is the first one, this is 39.241. You see that the offset and the gain both are slightly different for this thermocouple. So, in other words, the conversion formula from voltage to degree Celsius is different for this thermocouple as compared to this one, because the values are slightly different. You can see that it is so for almost all of them. So, all the 11 cases or 10 cases whatever we have got here, we have got the values of gain set here. In other words, this is the software which is going to do the background calculation. So, when the voltage is scanned or the several channels are scanned consecutively by the data logger, the first channel it will get the value in the voltage in the output in the volts value, and immediately it will use this conversion formula and convert it to the Celsius, that C is the Celsius and what is coming is voltage. So, voltage is converted to a Celsius. So, the temperature automatically is going to be recorded by using this particular formula. So, for each channel I can have a different formula, or it may be the same if they are all have the same constants or coefficients given here, they can be same. So, we can each channel I can have a different formula, and then I can convert the input to the channel in the terms of voltage to degree Celsius, and that can be done here. So, in this case I can follow the temperatures of these 11 channels independently at any given instant of time. Of course, I can instruct the data logger to scan each one of these channels at regular fixed intervals of time. I can ask it to do it every 1 second or every 5 seconds or every 10 seconds or every half an hour, whatever is the requirement we have in our particular experiment. If it is a fast experiment where things are changing very rapidly, I may ask it to scan it at a rapid pace. If it is a slow variation, I can ask it to scan it slowly over maybe 5 minutes, 10 minutes intervals. The point is, if you are scanning over a long length of time, the amount of data which has to be saved becomes very large. Therefore, I cannot for example, I cannot save data over one day by taking every second, it will become a very voluminous amount of data. So, depending on the experiment, depending on the amount of time you are going to conduct the experiment for, and depending on the requirement, you can scan. If it is very fast variation, you can scan faster or more at smaller intervals of time, or if it is a slow variation, we can do it at a slower or a larger intervals of time. In fact, what I have done is, I have also shown what other things can be done. You can see here that I can find out in this particular case, the data logger has got several types of thermocouples already built into it. I do not even have to do the calibration which I talked about. What I can do is I can simply tell the computer which type of thermocouple has been used, and I can, in this case the highlighted one is temperature type K. So, if I say type K here, automatically you do not even have to give the gain and the offset, you do not have to give it, it can actually be asked to do it by itself. That is, automatically it will determine what is the type, and it has a table of values corresponding to type K, and then it will compensate for the cold junction, and then automatically find out what is the temperature for a given input in that particular channel. So, these are all possible with the data logger. So, what we have tried to do is to just indicate how measurement is now done over a number of channels by using a simple data logger. Of course, the data logger costs a lot of money. This data logger, for example, costs about 50,000 rupees, and if you have a data logger, you can see the number of channels are there. The number of channels can be 16 or 64, 128 and so on. Different data loggers come with different number of channels, and as I indicated in the last lecture, the data logger also can plug into the USB port of a PC nowadays. The one which I have shown here does not do that, it has to be connected through an interface, and it has got its own controller and so on, but the new ones come with USB. You can communicate with the computer using the USB port directly. So, it is very plug in and play, as they say. Let me take a second calibration example. This is more like really what one would be doing in practice. If you are making measurement over a certain range, in this case I have taken the range between room temperature or 0 degrees and 100 degrees, and if you notice here, I have got a value around 30, another about 50, another about 75 or 80, and another about 90, and I have avoided using the end points. It is good practice to choose 4 or 5 calibration points or temperatures, in this case temperatures. It is valid for any instrument. If I am using a voltmeter, if I want to calibrate the voltmeter, I must calibrate not at the extreme points. Extreme points are not reliable. What I have to do is I have to take 10%, 30%, 50%, 70, 80, like that. We have to take several points in between the minimum and the maximum, and then use the calibration if it is a voltmeter. If it is some other meter, exactly the same thing. If it is a flow measuring device, for example, I would not go to the extremes, I will only do it in between the range. So, this range will be known to us, and therefore, we will pick up the values like this. In this case, you can see that there is a difference between the thermocouple. This is a shielded thermocouple, stainless steel shielded thermocouple, K type I think, and this is the standard thermocouple. That means that I have taken the reading from a handbook which gives the data for this particular type of thermocouple, and I have compared the two. That is exactly what I have done, and I am giving you the value of the voltage which is converted to the temperature, and I have plotted it here, and you can see that there are some differences, and of course, this is for a particular thermocouple. Another thermocouple may show slightly different behavior, and if I plot the error, you can see that the error is almost 10% here, and of course, it becomes small between 40 and 80, it is about 2 to 3%, 2% or so. So, what I can do is I can use this value as a correction. When I am making actual measurement, the data in this form, error plot useful for the particular range, I am using this in the particular 40 to 90 degrees is where I am going to make the measurements. I can use this relationship, this information as a correction to correct the information or correct the temperature obtained by using the thermocouple and make it agree with the standard thermocouple. So, this is real calibration, where I am trying to bring it in agreement with a standard reference thermocouple. The other one was utilitarian. This is a slightly different way of doing the same thing, but we are comparing a thermocouple of the same types for which the output is known. So, I would like to use the table for the purpose of determining the temperature. The next one I am going to look at, the next case, is a calibration of flow meters. In fact, we discussed several types of flow meters earlier, and I am not going to discuss any particular flow meter. I am just giving a schematic of how one goes about calibrating flow meters. So, we may have either glass flow meters or liquid flow meters. I am avoiding solid flow meters or solid flow, that is another thing altogether, for which I am not going to spend any time in this series of lectures. The gas flow meters can be either volumetric or it could be gravimetric, that means mass flow or the volumetric flow, and liquid flow meters again you can have volumetric or gravimetric. And if you look at the gas flow meters, when you have a volumetric flow rate, the difference between liquid and gas is that liquid can be collected easily and it can be measured. That is what I am doing here. I am collecting the liquid for a certain length of time in a tank whose volume I can easily measure. For example, I can have a beaker and in which I can collect the water, or I can have a bucket in which I can collect the water and weigh the bucket before and after collecting the certain volume of liquid which has flown through the system. So, by measuring the volume, if I know the density of the material of the liquid, I can find out what is the volumetric flow rate, or I can directly find out by weighing it, I can find out what is the mass flow rate of the liquid. So, these are the two methods which are available, and both of them depend on simply collecting the liquid which is flowing through the system or through the flow meter for a certain period of time, note down the period, and in fact this is an absolute calibration, because we are actually measuring the volume, actually measuring the time for which the volume flow rate has occurred, and dividing one by the other we will be able to get absolute value of the volumetric flow rate. So, this is direct calibration. If you come to the case of the gas flow meter, what one does is you have a burette, highly accurate bore, so that the burette I can measure the volume swept by the liquid by the gas. How is it done? A soap film is allowed to get into the system and the gas simply displaces the soap film, and you find out the amount of time taken in sweeping a certain volume of the burette by the soap film, and that is the volume flow rate, volume flow for that particular period of time, and all I have to do is to divide one by the other, I will get the volume flow rate. So, by knowing the actual volume flow rate by this method, I am calibrating the instrument, because the instrument will indicate something else. The instrument will give you an output in the form of an voltage or a delta P. So, I can now relate delta P directly to the volume flow rate or the mass flow rate, as the case may be. So, let us take one or two examples how they can be done. This is a case where gas flow meter is calibrated. So, I have the Matron test. This may be any meter, for example, a rotameter, and then I have gas supply. It may be air, in which case it will be air supply. If it is gas, you supply the gas and it flows through a vertical burette, and I have a soap solution here, and I will at some particular time I will allow a soap bubble to enter, soap film to enter, and then the gas flow is going to carry this film across this one, okay. And there is a photocell here. When the soap film crosses that, the timing device will start, and when the soap film passes the next photocell, the timing device will stop. So, the time duration over which the soap film has crossed, has travelled from here to here, is noted by the timing device, and the volume of this vessel or the burette between this point and this point is predetermined or known earlier, which can itself be measured by using water or liquid and then filling that and then determining the value of the volume by using an accurately calibrated beaker or some such arrangement. So, you see that we are measuring the volume swept by the gas as it flows through the thing, and the same amount of gas must have passed through the gas of the meter, and the meter on test I can determine the flow rate of the through the meter on test by measuring this volumetric flow rate, and whatever is the output of the meter on test will be corresponding to that particular volume flow rate. So, what normally we do is we vary the flow rate, as I said, maybe 30%, 50%, 70% of the range, and then for 3 or 4 values I can do the calibration. The second method, which is very simple in the case of liquid flow, is there is a pump, there is a sump here, the liquid is circulated, it goes to the test meter, and then it either can go into the weighing tank or it can go to the sump. So, what I have here is a diverter or a control valve system. So, what it does is it will either send the fluid to this side or this side by opening very quickly a quick acting control valve. So, it will either flow this side or this side, it will either go back to the sump or go into the weighing tank. What we do is we start the measurement process by allowing it to come to the weighing tank, and after a certain length of time you stop it and divert it back to the sump, and you find out how much liquid has been collected in the weighing tank, either weigh it using a weigh bridge or you measure the volume by noting down the volume of the water or the volume of the liquid which has been collected. So, you see that the volume divided by time will give you the flow rate, and test meter will indicate whatever, maybe it is a delta P or some other signal, voltage signal. So, you can see that there is a correspondence between this value, the value indicated by meter, and the weighing tank measurement system. So, this is one way of calibration. So, in fact, I have shown as an example here. I am trying to calibrate a rotameter, and essentially we have set up a similar setup, and then the calibration looks something like that. So, we have the measured value of the flow rate, liters per minute, and the water flow rotameter reading. Rotameter is calibrated and the scale on it says whatever is the value, and you can see that there is some systematic variation between the two. The measured value, which is measured by using the absolute method which I talked about, collecting a certain volume of the fluid liquid and for a particular amount of time, that is compared with the reading indicated in the rotameter, and you can now see that there is a more or less a good comparison, but of course, there are some variations which can be used as a calibration information, or you can use correction factor for that. As you can see here, for example, here the reading of the actual measured is smaller than the indicated by the water or the rotameter, and here it is the opposite. So, the error is both positive and negative in this particular case. The third example I am going to take is the measurement of small differential pressure, delta P, very small delta P. Typical application, of course, is the measurement of velocity of air in a duct or a wind tunnel, for example. When you want to measure very small pressure differences, there are several options, and I have only given 2 options here. One is I can use a mechanical arrangement which is simply a manometer, which is called a Betz manometer. This is one option. Otherwise, I can use a pressure transmitter with a small range. So, the range I am going to determine by using the data from the typical application. In the application, I will know what is the range of the velocity I am going to measure, and then I can convert this velocity information to a suitable information in terms of delta P, that is where the pressure transmitter is coming, or it would be a delta P where the bed manometer is going to measure the delta P, and both of these I am going to discuss in some detail. So, what I will do is I will go to the board and look at a typical example. So, let us look at a typical example of delta P measurement. This will correspond to the measurement of a velocity, measurement of air velocity. The instrument I am going to use, or the primary instrument I am going to use, is a pitot-static tube. Of course, we have discussed it earlier, it is nothing new, we know about this instrument. So, what I am going to do is I am going to just describe a typical situation and find out what are the typical values of the velocities I am going to measure, and then accordingly we will find out what is the suitable instrument for that particular purpose of measuring the delta P. So, I will consider air as the flowing fluid at 25 degrees Celsius, because the flow rate is dependent on the density, and I will assume that it is at 1 atmosphere, very small difference with respect to 1 atmosphere, because delta P is there. So, the delta P is very small compared to the atmospheric pressure. So, the maximum velocity I know is about 10 meter per second, and the minimum velocity is about 0.5 meter per second. This is the measured value. I am going to measure such values. In fact, I can find out what is the dynamic head. If you remember, if you have a pitot-static tube, I may be using water as the manometer liquid, and therefore, it will be convenient to represent the reading of the pitot-static tube in terms of millimeters of water or millimeters of water column, that is delta P in millimeters of water column. So, let us look at the values. The dynamic head we know is what is going to be indicated. This is nothing but delta P is equal to half of rho u squared, where rho is the density of air or the fluid which is flowing. This is the velocity, and in fact, all I have to do is to calculate the delta P max and minimum. This will be half into rho of air. I can calculate using the ideal gas relationship. So, P is 1 atmosphere. So, 1 atmosphere 1.013 into 10 to the power of 5 pascals, and the value of R is 287, and temperature 273 plus 25. So, I can just put the value as 298. So, this gives you a value of 1.184 kg per cubic meter. So, all I have to do is to introduce here into 10 meter per second is the maximum velocity, 10 squared. This will be in pascals. This gives you a value of 59.2 pascals. I can similarly determine the minimum pressure which is going to be measured. All I have to do is to change the velocity to 0.5 meter per second into 0.5 squared pascals, and it comes to 2.37 pascals. So, we are talking about very small delta P. In fact, I will convert this to millimeters of water. So, delta P is equal to some rho g into h, where h is the water height of water column, g is the acceleration due to gravity, and rho is the density of water. I will take density of water simply as 1000 for the sake of simplicity. So, delta P max will correspond to H max, which will be delta P divided by, so delta P is 59.2 pascals divided by 1000, that is the density of water, into 9.8, and to convert it to millimeters, I will multiply by 1000. So, actually it is like these two will cancel, it is simply you divide this by 9.8, you get that value, and that happens to be 6.043 millimeters of water. So, the maximum we are going to measure H max is 6 millimeters, and I can also calculate H minimum, that will be simply the value of delta P in pascals, 2.369 divided by 9.8, so many millimeters of water, that will be 0.242 millimeters. So, you can now see what is the kind of number we are going to be measuring. We are talking about very small changes in H. So, one option is of course use a Betz manometer, where we use an optical arrangement to measure delta H with a high degree of resolution. So, let us look at a typical schematic of a Betz manometer. It is actually basically a well type. Instead of U tube, there is no U tube, there is a vertical tube sitting into the well. So, it is actually a well type manometer. So, we have the well here, that means it is a very large reservoir of water. I am going to use liquid in the form of distilled water, and what I have is a tube which is sitting in the middle of that, and the space above the well is connected to the higher pressure P1, and the space above the column above this vertical tube is connected to the second pressure, the lower value. Okay. So, this will be what I am measuring is the dynamic head, and which is now in the form of P1 minus P2 related to H here. This H is the height of the column, the height difference between the two sides. And how is it measured? I have a float. This float is going to be following, it is going to stay at the meniscus of the water in this tube, and to the bottom of the float is connected a glass scale, which is dipping into this chamber here, the lower chamber. This is a small tube into which this glass scale is going to be dipping in. And what I will do is, I will use a lamp, some two lenses here, and using the eye I can focus on the scale. I can put a spot on the scale, that is the spot I have talked about. And you have a vernier which will indicate the value of the height. In this case I have just simply shown 42 point some 4 or 3 or 4. So, this is so many millimeters or so many whatever units of water column. So, you see that what is being done is the height of the meniscus is measured by having a scale floating, a floating scale. The scale is actually floating because there is a float here, and the scale will go up and down, and the marks are on the scale corresponding to the main scale division, and the other one is the vernier, which is projected by the optical arrangement, and therefore, what we do is we measure the two in this particular form. So, you see that the delta P can be measured with very good resolution. It is supposed to be possible to measure up to with for example 0.02 millimeters of water column. So, this is a very standard equipment which is usually found in laboratories where wind tunnel work is done. The next one is a more interesting case. In fact, we have come back to this, we are coming back to this particular sketch. In the last lecture also I talked about the current loop, 4 to 20 milliampere current loop, and what I am doing is I have a pressure sensor with 4 to 20 milliampere current loop, and the pressure sensor is now capable of measuring 0 to 10 millimeters of water. If you remember in the example which I worked out, it is about 6 millimeters the maximum. So, we have 0 to 10 millimeters as the range of the pressure sensor, and the pressure sensor is going to be transmitting the pressure signal in the form of a 4 to 20 milliampere current. Okay. This current is maintainable by using a power supply, as I indicated in the last lecture. It can be either 12 volts or 24 volts or some such power arrangement, power supply of such voltage. In this case, what I am doing is at the downstream end I have a digital voltmeter or voltmeter in general, and I have connected a load resistance of 500 ohms. Okay. The 500 ohms is the load resistance which is going to be here. So, the minimum reading I am going to get of the voltmeter corresponds to 4 milliamperes, and the maximum will correspond to 20 milliamperes. Okay. So, we can work out easily what are the voltages which we are going to get by using these numbers. So, I will go back to the, so we have either we have a current equal to 4 milliampere, this is the minimum, and the current maximum is equal to 20 milliamperes, and I am using a 500 ohm resistance. So, we can simply use Ohm's law. Resistance is 500 ohms. So, I can calculate what is the corresponding voltage values. Voltage minimum is simply IR, 4 into 10 to the power of minus 3 into 500. So, this will give you 2 volts, and the V maximum will correspond to 20 milliamps, this will correspond to 10 volts. So, the output of the instrument when delta P is 0, that means there is no flow in the wind tunnel. So, delta P equal to 0 translates to 2 volts output, delta P equal to 10 millimeters of water. In this particular case will correspond to 10 volt output. So, it is a very interesting example. Now, I can convert, in other words, the voltage output into a resolution value. What is resolution? So, let us look at that. The resolution, of course, in this particular case will depend on how I am able to measure these voltages. What is the resolution of the voltage measurement? That is the choice of the particular voltage measuring device. Suppose, for example, I am able to measure 0.01 volt resolution. Just an example. That means what does it mean? I can go up to 19.99. You realize that there are 4 digits, 4 numbers here. The first one is half digit because it can go to 0 to 1, the other 3 can go to 0 to 9. Okay. This is 3.5 digit resolution. But the point is not that. Point is, what does this correspond to? So, we have, in this case you can see that the 4 milliamperes correspond to 0, 10 milliamperes, 20 milliamperes will correspond to 10 millimeters of water. Okay. So, we have 10 millimeters of water corresponds to 20 milliamperes, which now corresponds to 10 volts. So, you can see that at the other end we have 0 millimeter of water corresponds to 4 milliamperes, this corresponds to 2 volts. Okay. So, we can now forget this. We now have a transfer function or transform from the pressure reading to the voltage reading. So, you can see that 10 millimeters of water corresponds to, actually the difference is 8 volts. So, corresponds to the difference. I am talking about the difference in values. So, the value is 8 volts will correspond to 10 millimeters, and therefore 1 volt will correspond to, you can find out, 10 by 8 millimeters of water. So, 1 volt. Now, depending on, if I am able to measure 0.01 volts, this is divided into 100 parts with 0.01 volt resolution. That means, I am going to divide this by 100. So, 10 by 8 into 100, see 1 over 80 millimeters of water, slightly less than 0.01. Okay. Slightly less than 0.01, because 1 over 80 is less than 100. Therefore, so you see that in this particular case, by using a 4 to 20 milliampere current output and using 500 ohms as the load resistance, I can actually have an accuracy of a resolution of 1 over 80 millimeters of water column. That means that I can measure. So, you can now see this 1 over 80 meters of column must correspond to a certain velocity change. Of course, velocity is non-linear. Velocity there goes as square, here it is going as a linear scale, right, because this is the, after conversion delta p only I am doing this. Therefore, when I want to translate this to a certain least count in terms of velocity, I will have to work backwards and find out what this 1 over 80 millimeters of water will correspond to in terms of the velocity which is resolved. I will leave this as an example to be carried out by the student, can work it out. So, what we have tried to do in the lecture number 49 and lecture number 50 is to just give a flavor of what is required in the laboratory. We have not actually done any experiment, or we have not shown any experiments in the laboratory. What we have done is to describe various methods of measurement, the characteristics of these, the errors, the analysis of errors and so on, and however, we never did any experiment in this particular course of lectures. Therefore, the student will learn whatever you have told here in this lecture series. It will become clear only when you go to the laboratory and make your hands dirty, work with instruments, and you will immediately see that when even for a simple measurement of voltage or a current, there is a lot of involved, a lot of things are involved, and one has to do a lot of work before one can set up an experiment in the laboratory. I hope we have been able to give a flavor of what is required, and it is up to the student now to go to the laboratory and learn some of these things by actually doing things by hands on experience with instruments, and we have discussed quite a few of them. I hope the student will do that to gain the actual knowledge through experimental methods. Thank you very much.